In this video, we are going to go over combustion analysis and how you can use a combustion reaction to determine the empirical and the molecular formula of a hydrocarbon. So I'm going to go through some easier examples, and then the last example, if you've paid attention to the first examples, the last one, if you can understand it, then I think you've got a good grasp on combustion analysis. But the last one is definitely a hard type of problem, so make sure you get these first two easier ones down. So combustion is just going to be a reaction between a hydrocarbon, which definitely has hydrogen and carbon in it, but sometimes has oxygen and sometimes even nitrogen in it, and it is going to react with oxygen in the air, and every single time it does that, it's going to produce carbon dioxide and water, and then maybe some other products, but we always have carbon dioxide and water. And what you notice is that the carbon from our hydrocarbon, all of it ends up in carbon dioxide, and then the hydrogen in our hydrocarbon always ends up in water. And so what we can do is use simple molar ratios in order to figure out amounts of C and of H. When it gets to oxygen or nitrogen, we typically have to be a little bit clever about how we solve for those values, and we'll see some examples with that. So here's how I do these problems. We have a 1.5 gram sample of unknown hydrocarbon, and it undergoes complete combustion to produce 4.4 grams of CO2 and 2.7 grams of water. And we want to know what is the empirical formula of this compound. So I'm going to first organize my thoughts, and we have C some number, H some number, plus O2, and it'll react in a combustion reaction to produce CO2 gas and water gas. And so I want to get a value for C and a value of H, and I'm going to use this relationship up here that all of the C's for my hydrocarbon are going to end up in CO2. So we have 4.40 grams of CO2. I know from just my experience in chemistry that when in doubt, go to moles. So you will come to learn that there's 44.01 grams of CO2 and 1 mole of CO2. And then we'll go one step further, but I want to do this as well for water. There's 2.7 grams of water here. Molar mass of water is 18.02. Now, here's a step that's different, is I don't care about CO2, and I don't really care about water. I care about carbon within the CO2, and then I care about the hydrogen within H2O. So I'm going to say in 1 mole of CO2, the ratio of CO2s to Cs is going to be 1. So there's 1 mole of C there, and then in 1 mole of H2O, there's 2 moles of H. So 1 CO2 has 1 C. That's the same thing as saying 1 mole of CO2 has 1 mole C. Same thing as 1 mole one H2O has 2 H's. 1 mole H2O has 2 moles of H. Okay, it's just a simple ratio. Now, when we solve this out, let's see what we get. We get 0.100 moles of C, and we get 0.300 moles of H. So now we've done mass to moles. We'll divide by the smallest. Here that's 0.1, and I get 1 for C, and I get 3 H's. So my empirical formula is CH3. Now, what you may be asking is, how do you know if there is oxygen present? Because if there's nitrogen present, we'd obviously see nitrogen somewhere in this equation, but we don't. So I'm going to show you how we see if oxygen's present. So I'm going to make this a little bit smaller. And here's what we can do. We know that this was 1.5 grams. So what I can do is I can say I had 0.1 mole of C, In 1 mole of C, there's 12.01 grams of C. And that gives me 1.201 grams of C. And then I had 0.3 moles of H. In 1 mole of H, there's 1.01 mole, or excuse me, not moles, but grams of H. And that gives me 0.301 grams of H. And if I add those up, I get 1.5 grams total. And so that's how I could tell you that there's no oxygen in that hydrogen, or in that hydrocarbon. So we're good. Let's look at number 2. We have, again, an unknown hydrocarbon, undergoes combustion, so CH plus O2 goes to CO2 plus water. And again, I don't know, this really could be CHO. I'm going to assume that it's not, because those are less common, but it still could be. I'll have to prove it at the very end. We'll see what we get. So we have 0.845 grams of CO2. There's 44.01 grams of CO2 for every 1 mole of CO2. And then in 1 mole of CO2, there's 1 mole of C. When I do that, I get 0.0192 moles of C. Then I have 0.173 grams of H2O. There's 18.02 grams of H2O for every 1 mole of H2O. And then in 1 mole of H2O, there's 2 moles of H. And I know I'm going quick through this, but it's the same process as what we saw in number 1. And I get 0.0192 moles of H divided by the smallest, which seems a little bit goofy here because they are the same. And I get 1. So my empirical formula looks to be CH. Okay, we'd have to be given the molar mass of the compound to turn it into the molecular formula. So let's do that step, that last step, just to prove that there was no oxygen. So to prove no oxygen in the hydrocarbon, we are going to take 0.0192 moles of C, and in 1 mole of C, there's 12.01 grams of C. I get 0.23 grams of C, and then we have 0.0192 moles of H. In 1 mole of H, there's 1.01 grams of H, so I'm going to plug that in, and I get 0.02-ish grams of H. We add that up, 0.25 grams total, and that adds to be what we started with, so I know that there was no oxygen in there. Okay. Now, buckle in, because 3 is probably the hardest these questions get. It's almost unnecessarily difficult, but if you can understand it, then I think you've got a good grasp of combustion analysis. So, we've got caffeine here. Caffeine is a stimulant found in coffee and some soft drinks and maybe some other things like even chocolate. And it contains C, H, O, and N. So, we're going to have C, H, O, and N. We're going to combust it, and we know we're going to get CO2, we know we're going to get water, but we've got to take care of this nitrogen, because carbon's taken care of, hydrogen's taken care of, and then oxygen has a place to go. But according to law of conservation of mass, we're not going to create or destroy elements in a chemical reaction, so we've got to have a place for nitrogen to go. And when we do this, they tell us, if you keep reading, we produce N2 as a product. So that takes care of where nitrogen is going to go. Now, we want to estimate the molar mass of caffeine. It lies between 150 and 200. So for me, when I read this, what I think it wants is, I think it wants us to figure out the formula, convert it to the molecular formula, and then once we know the actual formula, we'll just calculate the molar mass then. Okay? Now, a good trick here is if you're looking at the key posted online, I use milligrams. And while milligrams is what we're given, everything is in milligrams. And so what I would do, and we'll still get the same answer because it's just ratios, is I'm going to get rid of the milligrams and just call it grams, because I already said I need to write small, and there's 1,000 milligrams in 1 gram, and I don't want to bother with even writing that conversion. So what I'm going to do is I'm going to get my C's and my H's. On any combustion analysis, let's just go ahead and get our C's and our H's. So we have 1.813 grams here, and we have 0.4639 grams here, and then 0.2885 grams here. So 1.813 grams of CO2. There are 44.01 grams of CO2 in 1 mole of CO2. And then in 1 mole of CO2, there is 1 mole of C. So I will solve that in just a second. There are 0.4639 grams of water that is given. Again, me using grams is not going to change this. I know it was given in milligrams, but it's not going to change this. There's 18.02 grams of water in 1 mole of water. And then in 1 mole of water, there's 2 moles of H. So let's plug those into our calculator. I think things are going to get a little bit crowded, so I'm going to write them down and then box them because we will need them later. But 1.813 divided by 44.01. Okay, we get 0.041195 moles of C, and I'm going to box that for right now just so I don't lose it. And 0.4639 times 2 divided by 18.02, we get 0.051487 moles of H. Okay, so that part probably the easiest part of this question. Now, we have nitrogen as well, and 0.2885 grams of N2. There's 28.02 grams of N2 in 1 mole of N2. And don't overthink this, just in 1 mole of N2, there's 2 moles of N. Okay, we just care about N because even though it's diatomic here, that's nitrogen when it's all by itself, so we know it should be diatomic. But here, it doesn't have to stay diatomic when it's bonded with something. So when we do that, we get 0.2885 times 2 divided by 28.02, and we get 0.02059 2 moles of N. Now, this is always the hardest part of a question like this. How do we figure out the amount of oxygen? And here's what a lot of people will say, and I'm going to write it out. I don't need you to write this part out, so I'll put it in red. That way you know not to bother writing it because it will just take up a bunch of space. Is people would say, oh, well, let me just take 1.813 grams of CO2. Say there's 44.01 grams of CO2 in 1 mole of CO2. And then in 1 mole of CO2, there's 2 moles of O. That makes sense. That'll tell me how many O's. And then they're like, oh, well, that can't work completely because there's also O's in water. And again, I'm taking the time to explain why this is not going to be good, so you don't make this mistake on a test or quiz. We get 0.4639, 18.02 grams of water for every 1 mole of water, and then 1 mole of water is 1 mole of O, so we get some number moles of O, and then some number moles of O. We could add them together to get our total moles of O. And you could say that we'd be off to the races. But I'm going to tell you that that is wrong. And here's what we need to look at. Some of these O's are from here, and that's what we care about. We just care about the O's that came from caffeine. But if you look at the reaction, some of those O's just came from the air, just the oxygen in the air. And I don't care about. Okay, I don't care about however many we had there. Okay? And what you're going to struggle with is, because this is not a balanced chemical equation, because we don't know what these numbers are, the total moles of O is actually not important to us to solve this. So what we're going to do, and we do this a lot in chemistry, is we're going to recognize that we know a lot. We know, and I'm going to switch back to blue, we know that we have C, H, O, and N. And so if I subtract, let's say this was, how much was this? 1 gram, 1 gram of caffeine. And if we subtract away carbon, however many grams of carbon we had, we subtract away hydrogen, our grams of hydrogen, and we subtract away our grams of nitrogen, which we actually already know that was given as 0.2885, we're going to be left with O, or our grams of O. So what I'm going to do is I'm just going to take these two numbers, I didn't copy that. Let me try that again, or else I will write it. And we're just going to get the moles of those. And then I'm going to plug in those numbers, and we should be off to the races. So 1 mole of C is 12.01 grams of C. Then 1 mole of H is 1.01 grams of H. I get 0.49475. I mean, I could keep going. It's probably not necessary. And then 0.051487 times 1.01. I get 0.0520 grams of H. I'm going to plug those in, 0.49475. 0.0520. And what I get is I get 0.16475 grams of O. Now, we'll just do our normal steps from here. We've done all the hard steps. Think back to what you know. We've got 0.16475 mole, or not moles, but grams of O. In 1 mole, oops, I keep goofing up. There's 16.00 grams of O in 1 mole of O. And we get 0.01297, I guess, moles of O. We've done mass to moles. That just took a while. We're going to divide by the smallest here, which, double checking, that is O, so we'll divide by 0.01297, 0.01297, 0.01297, 0.01297. We get 1. 0.020592 divided by 0.01297. Did I plug in something wrong? Let me check one thing. 0.020592 divided by 0.012. 0.02059 divided by 0.01297. I should be getting 2 here. I'm going to go back and check what my problem was if I messed something up. 0.051487 divided by 0.01297. You get 3.96, which is 4 because it's within 0.1. 0.041195 divided by 0.01297. And on this one, we should be getting 4. So I think what my problem is, and sometimes this happens, is because we have so much, can't remember if I plugged in things right in the calculator. I'm pretty sure I did. If we just cut those off just a little bit, so this might be 0.0412. And this would be 0.2059, and then that 7 there is causing issues. On the test, I make sure all the numbers would never even potentially be problematic like this. Oh, and my H's, see, when I plug in the H's again, 0.0514 divided by 0.0129, 0.051487. 4. So let me see. Okay, this should be 5. And again, I'm struggling because I'm making this video and I want to get it right. Trying to find my mistake. Just a simple calculation mistake. Okay, anyway, just trust that those numbers, I can't find where, I think it's just one number I goofed on, one calculation. Anyway, trust that those are right. My empirical formula is C4H5N2O. And if we go ahead and get the molar mass of that, you get 97.11 grams per mole. If you remember what we were trying to solve for, is we need a molar mass between 150 and 200 grams per mole. So the only way to get this 97 within that range, because we can only multiply by whole numbers, is to multiply by 2. When I do that, 97.11 times 2, I'm going to get 194.22, which means, and that would be the answer because that's all that they asked for, that caffeine has a molecular formula of C8H10N4O. So if you are able to find where my mistake was here, because I'm going to stop the video, just go ahead, send me a Schoology message with where the mistake was, because I know what I put here with 4 carbons, 5 hydrogens, 2 nitrogens, and 1 oxygen is the right answer. And when I did it on my own, because I'm looking at my key, that's what I got, and I just know that that's what caffeine is. But if you can find my mistake, just go ahead and send me a Schoology message, and if you're right and it makes sense to me, I will give you bonus points.